Hey, welcome to another lecture on logarithms. In this video, we're going to talk about how logarithms can help us solve exponential problems. All right, so let's just return to our COVID example. Okay, so let's say it's day one and you have 1,000 people infected. And there will be a shutdown if, let's say, 1,000,000 people are infected. So this would be in some state large enough where 1,000,000 people is a significant amount, but maybe not that significant. Like, I don't know, New York, 1,000,000 people are infected, you probably shut it down in an instant. All right, so if the growth rate is 1 in 20, so that's approximately 0.05. How many days away from a shutdown are we? Well, we're first going to start with our COVID model. So we'll say the infected on day T is, we start with the number that we already have. So that's our initial amount. And we're going to assume we have an exponential model in this case. So that'll be E to our rate, which is 0.05 times time. Notice this is actually like the exact same formula as interest is growing as well. So basically they're the same problem. You could rewrite this whole problem just as an interest problem. If you had like an investment where you start with $1,000, you want to know how long it takes you to get to 1,000,000 and your interest rate is 0.05. All right, so now we just want to solve this problem. So we're trying to find T when we have 1,000,000 on the left equals 1,000 e to the 0.05 t. We're going to start with our usual steps of solving problems, which is, we're just going to clear out this 1,000. All right, so nothing new so far. And now that simplifies to 1,000 equals e to the 0.05 t. This is where we have to introduce something new. We need to undo this exponential. And so to do that, we need the inverse function. And you would tell me that that inverse function is log with the base of e because it's raised to the e of x. And in math, we abbreviate that to ln of x. The ln of x, it means natural log of x. It's ln because it's in, I think, Greek, it's logarithmus naturali, or something like that. Cool fact, if you look it up, well, I guess it's not that cool, it's just, that's why it is. All right, so we just apply that to both sides. We just apply the inverse function to both sides. And we're there. ln of 1,000 equals ln of e to the 0.05 t. All right, we stick with ln of 1,000 on the left. But over here, these two cancel with each other and we just drop down with a 0.05 t. We want to undo this 0.05, so we just multiply 20 to both sides. And we get 20 ln of 1,000 equals t. And this is a good time to break out your trusty calculator to figure out what ln of 1,000 is, which I'll do right now. Right, so the interesting thing about logarithms is how slowly they grow. You might think ln of 1,000 is a big number, but it's actually about 6.9. That's kind of an artifact because of how fast like the exponential grows, that if you're undoing it, it's going to go really slowly, or it's going to be really small, because you don't need a big number. You don't need to plug in a big number to e to the x to get 1,000. So when you're undoing e to the x equals 1,000, that x is going to be not that big. And so we get 138, which is actually kind of fast, because that's 1,000,000 is 1,000 times bigger than 1,000. So it only takes 138, this would be days, for our infection to grow 1,000 times in size. So that's still pretty crazy. And that's with only a person infecting someone else, with probability 1 in 20 each day. All right, so this is the typical way, though, that we use logarithms to solve these modeling problems, where you're going to isolate your exponential, like e to the 0.05t on one side, and then just hit both sides with a logarithm. And then we use that inverse property to pull the 0.05t down. All right, I think I'm going to end it here. All right, see ya.